Hello and welcome to the August webinar from the IEA Clean Coal Centre. My name is Ian Barnes and I'm an Associate Consultant to the Clean Coal Centre. Our monthly webinars are based on our technical reports which are available from our website, which is www.iea-coal.org. And if I could remind you that residents of member countries and employees of sponsoring organisations can download the reports at no charge after a one-off registration. Please feel free to visit the website for more details of this service. My webinar today is on operating experience of low-grade fuels in circulating fluidised bed combustion boilers. The report of this study has just been published and is available for download on the Clean Coal Centre website. If you have any questions during the talk, please use the Ask a Question box at the top of the screen. If you'd like to add your email address as well, I'm happy to follow up with a fuller answer should we run out of time. Okay. Right, the aims of this particular study are summarised in these 4 points here. We set out to give examples of the range of low-grade fuels, their reserves and properties that are co-utilised with coal and burnt as individual fuels. We then went on to review the issues for CFB plants in utilising these particular fuels, which can be quite challenging. The report then presents selected examples of manufacturer and operator experience with purpose-built plants or modified CFB plants. And finally, the report presents an up-to-date global inventory of CFB plants using a range of low-grade fuels. So the first question to ask ourselves is, what are these low-grade fuels? Generally speaking, they're characterised by having a recoverable energy content, but one which is lower than the range expressed in the normal fossil fuels, oil, gas and coal. Additionally, they may be very high in inert materials, principally mineral matter and moisture, and this in many cases accounts for their very low as-fired recoverable energy content. Vanillin, they may have high concentrations of pollutant precursors. Sulphur is a particularly good example of this, but I'd also cite things like vanadium in petroleum coke by way of example. So, what are the attractions of low-grade fuels? Excuse me. Primarily financial. They're a resource with recoverable energy. They're available at a relatively low cost. They have an attraction for co-firing with coal, for example, when the price of coal is particularly high and decreasing the overall sort of costs of plant operation. Secondly, certain of these low-grade fuels may reduce emissions when co-fired with coal. This is particularly true of biomass and biomass-derived materials like waste wood, which being CO2 neutral can contribute to reduction in CO2 emissions from a coal-fired plant. Thirdly, they may be considered as waste materials in their own right, and very often, as a consequence of national taxation policies, these materials can have very high disposal cost. If these materials are used for energy recovery, this cost can be at the very least offset, or in some cases eliminated, by using that waste for energy generation. And finally, they may be useful in clean-up activities. For example, where old coal workings and spore heaps are being cleaned up. If the material can be used for energy generation, this can contribute positively to the economics of the activity. Now, this slide just gives a flavour of the very wide range of low-grade fuels that have been evaluated for energy production. They're grouped under these 5 headings: agricultural waste and biomass, industrial waste, municipal waste, wood waste and fossil fuel wastes. and the materials range from fairly sort of well-known ones like agricultural waste, biomass, through to quite esoteric ones that arise in very small quantities. But nevertheless, if the producer of the waste can realise monies from their use, this can be very beneficial to the business activity. Now, in the study, we reviewed the global reserves or annual arisings of these low-grade fuels under these 13 headings: biomass, peat, oil shale, lignite in brown coals, oil sands, coal mill washery rejects, petroleum coke, wood and fibre residue, refuse-derived fuel, plastics, sewage sludge, and high chlorine and high sulphur coals, the latter sometimes being known under the name of battle coals. Now, in some cases, the arisings of these materials can be very significant. For example, I'd cite petroleum coke or pet coke, where production is currently around 170 million tonnes per annum. And in the case of coal washery rejects, recent studies have estimated that up to 60 gigatons are available worldwide. So a very significant resource. Now, this slide just gives a feel for the wide variation in properties just under one category. This lists several types of biomass, and if you just look across the different materials, you can see, for example, that the ash content can vary quite significantly. But of particular importance, the elemental composition can vary very significantly. And this can have implications for plant operation in respect of fouling and slagging issues. Some of the materials are very high in the alkali metals, there's some 20% there, whereas others are relatively low, and in some cases more coal-like. Now, the technology that's been very successful in utilising these fuels is CFBC, hence the basis of this particular study. This slide shows a generic plant based on CFBC technology, just to remind ourselves of the basics. Solid fuel or mixture of fuels, along in most cases with limestone for sulphur capture, is introduced into a very large water tube boiler. Now, this contains a bed of inert material which is fluidised by preheated air, and it's in this space that the fuel burns and releases heat to the water tube walls. The fluidising velocity in the CFBC boilers is sufficient to actually entrain the bed and burning fuel and carry it out of the main boiler, where it's captured by a number of devices, finally a system of cyclones, and then returned to the bed via a separate leg. Hence the circulating aspect of the technology. Heat is recovered in the usual way with reheat and economizer sections. Steam is used to drive a steam turbine and hence a generator for power production. Heat is further recovered in the air preheater to pre-warm the fluidising air. And finally, on the back end, systems of pollution control can be installed for very low emissions. Now, CFBC is particularly suited for low-grade fuels for a number of reasons. The large inert bed provides a sort of a heat sink for operation, and this allows it to accommodate a wide range of fuel properties. Building on that, it's possible to change fuels sometimes quite significantly with respect to properties online with minimum disruption to the process. CFBCs operate typically at 800-850, and this lower combustion temperature reduces the potential problems from fouling and slagging, which can be associated with certain materials. And the low temperatures and the long residence times facilitate emissions control. This is particularly true in the case of sulphur capture with limestone. This figure here summarises the challenges that different fuels pose to operation on CFBC. Just to explain it a little bit further, if you look over on the right-hand side, this is really the standard design for CFB, where you see the coal types there, and also petroleum coke, very much a sort of coal-like material, indicating that pretty much unmodified plant can be used to accommodate these. But as we move over to the left for different waste fuels, the challenges increase and require ever-increasing modifications to the process and or the operation of the CFB to accommodate the fuels successfully. The most challenging fuels right over on the extreme left-hand side are materials such as municipal solid waste, refuse-derived fuels, and PVC. Right, just to look at some of the individual challenges from fuels. I mentioned earlier that these fuels can be quite high in moisture, although having said that, the fuel moisture content is generally, unless it's particularly high, not an issue for CFBC utilisation. That's just as well because it can vary quite significantly from a coal, for example, of good quality, having a moisture content between 6 and 7%, going up to certain biomasses which can feature up to 60% moisture. When you reach these highest levels of moisture, it's customary to use a support fuel, which could be coal, gas or oil, to support combustion. The heating value, well, the heating value of the fuels can vary very widely, and is almost always linked with the mineral matter and moisture content of the coal, of the fuel rather, as fired. As we saw previously, high moisture biomass can have an energy content as low as 6.5 megajoules per kilogram as fired, whereas something like petroleum coke can be as high as 32 megajoules per kilogram, which is really sort of comparable or exceeds good quality coal. When we look at the waste coals, coal washing residues, these can have very low energy contents, as low as 4.5 megajoules per kilogram. But the moisture content is correspondingly low, and the reason for the low heating value is really the dilution by the high mineral matter content. The mineral matter or ash content can vary widely, going from a good example, petroleum coke, pet coke. The ash content is typically less than 1%. Wood-fired biomass, also very low ash, about 2%. But as we saw earlier, the waste coals can have very high ash content, 60–75%. But because the moisture content tends to be relatively low on these, they can still be burned without support fuel. Sulphur and chlorine contents can be an issue in these materials, and again, wood-based biomass, very low sulphur content, but pet coke can contain 6–8% sulphur, and as we'll see later, some of the poor quality lignites can have sulphur contents of as high as 13%, which pose specific issues. Chlorine content is also an issue. This can arise in certain coal-derived materials, but the greatest challenges are provided in the refuse-derived and municipal solid waste-derived materials, where the chlorine content, can frequently exceed 1%, with implications for deposition and corrosion. Now, looking at some particular examples of operating experience and modifications, this slide shows a schematic of the B&W internal recirculation boiler, which has been developed to deal with a very wide range of fuel types, and has evolved based on the experience of burning that wide range of fuel types in a number of ways. The slides which follow will show how the capture of material leaving the main boiler has evolved through different types of design, specifically on what are known as the U-beams, which have been highlighted on the left here. Now, the boilers are noted for having a two-stage solid separator. This is the process by which the bed material, which is circulating, is captured and returned to the main boiler. And the primary mechanism for this is through impaction on a series of devices known as U-beams, which are located at the furnace exit. And these collect the bulk of the solids, 95 to 97%, and they are then returned to the furnace by gravity. Material which escapes the U-beam collection passes into a multi-cyclone dust collector in the lower temperature region of the boiler, and here the remaining ash is collected and again returned to the main boiler. Now, B&W's experience on the range of fuels has resulted in evolution of the U-beam separated design so that this degree of capture can be achieved efficiently with a range of fuels with additional benefits to furnace operation. If we look on this slide, we have the original generation, which featured, I think it's 11 rows, which were actually outside the main furnace, and an associated solids collection hopper for return of material. Evolution of this design led to the introduction of U-beams actually in the furnace, where material would drop directly back into the bed, but material which passes that is again collected in the hopper. And then further evolution of the design led to the introduction of a sort of a dogleg slope on the furnace exit, fewer U-beams, but very efficient collection, returning a very high concentration of bed material back into the furnace. This slide shows that process in a little bit more detail, where you can see the structure of the U-beams, where impaction reduces velocity of elutriated material, which then drops down back into the main part of the furnace. We have a set of U-beams actually in the furnace, and the backup second set lying a little way behind that. Another area of improvement has been the minimisation of refractory within the boiler. This has benefits from two standpoints. If the refractory is minimised, then the warm-up of the boiler is reduced, warm-up time rather of the boiler is reduced, and less refractory means less surface available for the potential growth of deposits, which can impede operation. So, summarising the lessons learnt from this exercise, the U-beam evolution design gives higher solids collection efficiency, better control of furnace temperature, the auxiliary power requirements were found to reduce, more uniform gas flow throughout the boiler, reliable operation of the solid separation system, the reduced refractory in the boiler has reduced startup time of the CFB. The CFB operates with a better dynamic load change and has a wide turn-down ratio of about 5:1. And there are several examples of this type of development in the bulk of the study, if you'd like to take a look. Second example, this is a CFB plant which was constructed and commissioned to utilise the Surat high sulphur Indian lignite. This is a particularly difficult fuel which has a high sulphur content of over 13% and requires a significant concentration of limestone for sulphur capture. Now, the operating experience of using this high sulphur lignite in the CFB, two problems really. Ash-related blockages were occurring at the cyclone, particularly at low load, where limestone, which had been calcined, was recarbonating and blocking up the entrance to the multi-cell cyclone system. Additionally, in the boiler back passes, deposition was very rapid occurring on the water tube walls there, and this was impeding the passage of flue gas, causing back pressure and operational difficulties. To tackle the cyclone deposits, program of work was initiated by the operators, checking the limestone feed size continuously with additional sampling, and optimizing the feeder size by fitting blanking plates to certain of the feed cells to make sure that the flow is consistent. The operating procedure of the plant was revised to maintain the higher combustion temperatures before commencing limestone addition to try and minimize this effect. And finally, with the incorporation of an air pulsing system at the junction of the cyclone and standpipe was found to be effective, disturbing the deposits at a very early stage. For the backpass deposits, a series of investigations using probes determined the rate and location of build-up, and a series of high-pressure soot blowers were introduced into this part of the boiler, and a fluidisation arrangement for smooth removal of ash falling into the ash hoppers to ensure that there wasn't really enough material for deposits to become established. Now, the outcome of both of these measures has been to improve full load operation, and limestone could be added sufficient to achieve a sulphur capture of more than 98%, which is quite impressive considering the very high sulphur content of the lignite fuel. This slide just shows the deposits that were occurring in the back pass of the boiler. There's a slide on the left before the introduction of soot blowers, and on the right after soot blowers have been introduced and operated, a nice clean flue gas path. And finally, the global inventory of CFB plants, which was carried out, this identified a little over 300 CFBC plants that were burning or co-combusting low-grade fuels, either alone or in combination with coal. Plants located in 33 countries, and the inventory gives details of the units, including the size, the commissioning date, location, plant owner, the fuel types that have been used, steam cycle conditions, and the pollution control equipment that's installed. Right, the key messages coming out of this study, summarised in the following slides. First of all, globally, there's a very significant resource which exists in the form of these low-value or low-grade fuels, and these are a valuable resource that is being increasingly exploited in combination with coal or fired separately. However, the properties of these low-value fuels can vary very widely depending on their origin. They can be high in inert components, mineral and water. Others contain elements which are deleterious to combustion technology and may indeed be pollutant precursors. But despite these drawbacks, the economic viability of their use has driven an increased utilisation of these low-grade fuels, and we believe this trend is likely to continue for the foreseeable future. We've seen how the CFBC plants are particularly well suited to burning the low-grade fuels or mixtures of these fuels with coal, for example, and other fuels. Having said that, it's not without difficulty, and fuel properties can be a challenge to the design and operation of CFB plants through low inherent energy content or the high inert material, plus components that can damage the boiler. We've seen examples of the way in which ash can be captured in the B&W boilers. We've seen problems associated with the high sulphur content of lignites. Other issues might include corrosion from the high chlorine materials that are sort of refuse derived, and these have all fed into evolution of successful CFB designs. So it's fair to say really that the CFB plants have risen to the challenge of using these fuels, and they are a really effective way of making the most of what would otherwise be problem wastes with their own disposal issues. Now, the publications that are associated with this webinar are two. There's the main IEA Clean Coal Centre report, which is available for download on the website, as I mentioned earlier. And there's also an executive summary in the form of the IEACCC Clean Coal Centre profile, which gives a two-page summary of the main points of the work. Okay, well that concludes the presentation. I'm happy to take any questions that might occur to you. So over to you. Thank you. Yes, I think we've got a question there. That's okay. And the question is, can you elaborate on possible problems when burning fuels with high potassium content such as straw? Well, the usual problem which is associated with the alkali metals, sodium and potassium, is one of deposition, where relatively low melting materials can form in the convective pass of the boiler. These can deposit on the heat transfer surfaces and act as, if you like, sort of sticky surfaces that aid the capture of ash. This can happen really quite quickly, so it's important to have systems in place to control excessive rates of deposition, and to ensure that your plant is appropriately designed with wide tube spacing, which gives compromise on heat recovery, but you have to trade off very often in dealing with these particular types of fuel. Okay, let's see if there's another one coming in. Yep. Could you say a little more about biomass fired with coal? Well, when you consider low-grade fuels like biomass and lignite, for example, these really are topics in their own right. And as you might expect, the Clean Coal Centre has addressed these through a series of reports over the years, which are available in the Clean Coal Centre library. So if you'd like to visit the website and take a look, I'm sure you'll find some very extensive treatment of these sort of specialised and large areas. Okay, just see if we've got any more. Nothing at the moment. Okay, so while I'm waiting to see if any more questions come in, if I can just draw your attention to the fact that the presentation which I've given will be available to download from the webinar page a little later on today. And the next webinar from the Clean Coal Centre will be presented by Mr. Kyle Nicol on Wednesday the 16th of September. And Kyle will be presenting on the application and development prospects of double reheat coal-fired power units. Okay, well that concludes things. I don't think we've got another question at the moment. So if I can thank you all for listening and bid you goodbye.